having, they call third place or interstitial fluid. So accumulation of fluid in here, water in here will give your patients that edema. And then during pregnancy is not a pathology, so you get to detect that due to elevation of estrogen level, and estrogen has to do with basically retaining water. So during pregnancy, we get to see elevation of estrogen to stretch uterus that is made of smooth muscles. But one of the side effects is that also it gets to promote water retention. So that's why in pregnancy we don't treat it. It's not a condition to be treated. But in other cases, absolutely, we get to have cardiac problems that can initiate that. We're going to have renal problems that can initiate that. So it is to be addressed. Now, you might ask, okay, how is it that is kind of complicated? It's not as simple as you're saying. So as far as interstitial fluid and capillary side is concerned, it's pretty straightforward. But once you get to cellular level, it gets a little bit complicated. And the reason is this. This membrane we call plasma cell membrane is actually called selective membrane. So it's a selective membrane, right? So what it means is that it's bilayer membrane in our cells. It's got all sorts of channels to regulate what goes into the cell and what comes out of the cell. So it's very selective. And whether you have any port as a channel like sodium potassium channel, or you have SYM port where you have a co-transporter like glucose and sodium. So that's a co-transporter. Or you have another one where it says you have what's called chloride shift, for instance, okay? So chloride goes in and bicarbonate comes out. So all of these specific channels, these are all under the influence of what's called, for the most part, many of them are like leaky. Leaky channels, not complicated. Whichever side has got greater concentration is going to promote osmosis, removal, diffusion, okay? But there are the ones that are under the influence of what's called first messengers. And that makes it a little bit complicated. So what it means is, I'm going to erase this over here so we can have a little bit more room. So what makes it complicated is that you bring in, so as let's say a cell membrane, when you have these channels, you're going to have receptors, okay? And those receptors are specialized to receive first messengers. So what is first messenger? This could be a hormone. So could be a neurochemical or neurotransmitters. So once received by this receptor, that's your first messenger, it will activate a cascade of reactions that can lead to regulating, let's say, for instance, calcium channels. So I'm going to make this short, not to give all the details for the sake of time. So once received, it's going to turn on G protein. And then G protein is going to go through certain chemical reactions, and then, for instance, cyclic AMP, and then cyclic AMP will regulate that channel. Okay? So the influx and efflux of calcium is determined. Is calcium electrolyte? Absolutely. Okay? So this is just an example of why at cellular level is a little bit more complicated than the exchange between interstitial fluid and capillary side. Because here, you don't have all of those selective membrane and channels and all that. But, so that's what makes it a little bit more complicated. Now I'm going to give you some examples of important hormones. So that's clinically significant to understand what's going on with your patient. So hormonal regulation of water and electrolytes. So remember that hormones are first messengers. So they get to target specific receptors on cell membrane, and then that dictates some channels. So, for instance, we get to have what's called atrial natriuretic peptide, called ANP, and that's released from atria of the heart. So once it's released, this is from atria of the heart. In response to hypertension. So the atria is going to be stretched, and then that initiates the release of AMP. AMP will target specialized channels called sodium channels at nephron level. And then as a result of that, you get to have sodium released. And then you probably remember this, that wherever sodium goes, water follows. So water is going to follow sodium. So you're excreting, by targeting those channels, you're going to excrete. Release, that means it's going to be going towards urine, right? So you're excreting that, and that means you're going to lose, so loss of water is accomplished. And then as a result of that, blood volume is decreased, and so is blood pressure. See that? So by controlling sodium, you get to control water. So you're urinating more, therefore, your plasma level goes down, blood volume goes down, and as a result of that, blood pressure goes down. So that becomes really important to regulate water and all that. So you could have an antagonist, yes?
Do you get to a point, though, where you're losing too much sodium?
Exactly.
Because of this?
That's right. So we have antagonist hormones. So the antagonist to that is aldosterone, which is another hormone, right? See, aldosterone, that is another hormone. This one comes from adrenal gland, okay, under the influence of angiotensin II, okay? So this one also targets sodium channels, but this one promotes sodium retention. That means you're keeping the sodium. So keeping sodium means what? You're keeping water. So that leads to water retention. So you're going to add that to your blood, right? So that increases blood volume. And then as a result of that, you get to increase blood pressure. So this would be antagonist to that. Can we have a synergist for this? Let's find out. So I'm just going over the most famous ones. So anti-diuretic hormone that is going to be released from hypothalamus. So hypothalamus basically will work with anterior pituitary to release ADH. So ADH targets, same deal. It goes to nephrons, but targeting different channels. So you're dealing with aquaporin, specialized protein channels called aquaporin. And then through that, we get to do what? Water retention. So we're pumping water back into the body, and as a result of that, it's going to be added to blood volume. And when you have increased blood volume, what happens? Exact same thing here. Increased blood pressure. So this would be synergist to aldosterone, antagonist to AMP. There are more, but these are the three major ones that we get to deal with, and that's how water is regulated. Now, one of the questions that I get is this. If I have water in my blood side or capillaries, and I have also solute, like sodium, why is it that dealing with net filtration pressure, I don't have any osmotic pressure coming from capsular side? Don't we have electrolytes in nephrons? We do. But the reason why you don't get to see a force like that in capsular side is that nephron will reabsorb, let's say, proximal convoluted tubal part of the nephron will reabsorb sodium and send it back to blood. So although you have it, you're not going to keep it, you're going to send it back to blood. That's why you end up with more electrolytes here as osmotic force than you could ever encounter in normal circumstances in your nephrons. That's why it's not part of the formula. You don't see it as part of the formula. So that's pretty much highlights of fluids and electrolytes. And then I have some questions for you to work on, and then I'm ready to respond to your questions.